Cleveland, Ohio, and we look forward to a very interesting talk by Professor Rosenblatt. Thank you very much.
Hopefully a very interesting talk from us, for sure. Okay, let me just give you a warning up front. I'm going to move this a little bit higher up. I'm doing back-to-back talks, which is an effort, and I somewhat highlighted this yesterday. The first talk is going to be more about background in terms of treating surfaces. It might go over time a little bit. Presumably there'll be a very short break in between. I hope. Yeah. Okay, good. But the second talk will be shorter than the allotted time, so everything should work out to be approximately right. Okay, these are headshots of my group. Most of the photos were taken behind our building. Those that weren't, I sort of indicated where things were done. My grad student, Joe Pender, who was responsible for a lot of this, he was actually a Chateaubriand fellow at Paris 6 with Nanoimaging group for a while. And he's since been back, and I'll tell you during the second talk about some of the things that he's done. But the first talk is supposed to be mostly pedagogical. So earlier today, Oleg Lavrentowicz talked about anchoring strength, and I'm going to effectively reproduce some of the results. There's I guess, not a complete presence of coordination between talks. So you can imagine that you treat a surface with some which we refer to as easy axis. And there are various ways of doing this, and I'll show you many ways of doing this. If the liquid crystal director is not aligned along the easy axis but deviates, you can normally take the free energy and do an expansion in powers of phi, which I'm using for azimuthal angle, and theta for polar angle. The anchoring strength coefficients, W2 phi and W2 theta, are normally called the anchoring coefficients. Sometimes you need higher order terms for very, very large deviations. And I believe a couple of days ago you heard Professor Yokoyama. He actually had done some work, in some cases showing that the W2 terms don't exist. But basically, throw away the W4s, what you actually have here is something that looks Hookean. Also, the extrapolation line that Oleg alluded to earlier, you can imagine that the liquid crystal along these lines will align like this, along this easy axis of lines like that. But let's say you put a sharp bend into things over here. Now the liquid crystal is not going to be able to follow this very, very strongly because there's an elastic constant that's going to try to spread out the orientation. It's going to bend more slowly around here. And as a result, you have this concept called the extrapolation length, L, which has dimensions of length, that's an elastic constant divided by that quadratic anchoring strength coefficient. If the anchoring strength coefficient is large, then this is going to be a small number, and that's because the liquid crystal director will be pinned down very, very tightly to the easy axis. Okay, now in terms of creating alignment, there are a zillion techniques. I want to go through them relatively quickly and then sort of go into how one actually does the patterning at the nanoscale. Sort of an old standby for many devices, at least up through about 10 years ago or so, was to put a polyamic acid down on a surface, bake it, imidize it, and then use a rotating cloth. It could be cotton or some other material. This is what we have in our lab. It's more just for research. It's not an industrial-sized machine. This rotates as the sample runs underneath, and then you can do an AFM picture to see the striations that occur when you do that. Now, the alignment mechanism, when you rub, this has been something that there's still disagreement about in terms of what's the most important. But the original model that at least I know of was by Dwight Barrowman and PRL back around 40 years ago. And he said that if you have a striated surface, you can imagine that if the liquid crystal molecules were aligned into the screen over here, there'd be no energy cost to have them fill up all space on top of the surface. But if you made the liquid crystal molecules like in the plane over here, and they'd have to follow this pattern, this topography, there'd be an energy cost associated with that. And you can calculate the difference in the two orientations and come up with some sort of characteristic free energy for having these grooves over here, which is related to the inverse thickness cube, I'm sorry, the inverse period cube of this, of the topography, and the elastic constant of the liquid crystal and the amplitude of the topography. And that actually turns out to work pretty well. But then in the late 80s, there was a group from AT&T, Bell Labs, I'm not sure anybody's there right now, where if you take and you rub a polymer, you're not only creating the grooves, but you're also realigning effectively the polymer backbone. And when you put the liquid crystal down on top, you have anisotropic van der Waals interactions that cause the liquid crystal to align along the polymer backbone and then grow epitaxially up from the surface to get a uniform surface. We did an experiment, I guess now 13 years ago, where we did this sort of rubbing technique, it's sort of a gross technique in a sense, at different temperatures where the sample itself was being rubbed. And you see over here that when the rubbing took place at a higher base temperature, you ended up getting more order, and it turns out that this gets very, very large as you go up toward the glass transition temperature of the polymer, and that seems to be an important prospect going on. Now, that's for uniform orientation. There are other methods I'll get to in a bit. I want to go on to patterning and then eventually nanoimaging here. The rubbing technique creates dust. There are all sorts of problems. So about 20 years ago, Kai-Shun Yang, then at IBM, he then went back to Taiwan and became, I think, vice president of Hanstar, a large display manufacturer, and now is retired. Worked with a combination of rubbing and also using masks for photolithographic step, and was able to get some reasonable alignment, sort of pixel by pixel on a pattern basis. But about the same time, a group at IBM in Zurich, Martin Schadt, and I'm not sure what happens to the others, Chigrenov is now in Hong Kong, they actually did use linearly polarized UV light to photopolymerize the polymer along a particular direction, and they found that that was able to give them alignment, and it was a clean approach. They went on a little bit later, a couple of years later, to show that if they came in at an angle with the light, they were able to get a pre-tilt. Has pre-tilt been talked about here? Does that sound okay? So the idea is that you can have orientation typical, this is planar or homogeneous sometimes it's called. This is typically vertical or homeotropic alignment. Very often, for device purposes, you want the angle at something other than 90 or 0, and that's one way of controlling it. Okay, so there are other techniques that came about, effectively based on light. You can see here, people use holography. They come in with two beams of the same polarization, and they create a system where the polarization is uniform, so they get the same alignment, but they can vary the intensity, and in doing so, they can create some sort of periodic alignment pattern. It's also possible, and I think this afternoon we're going to be hearing from a completely different topic by Bob Pelkovitz. You can also use different polarizations. Here, these are linearly polarized light. This is circularly polarized light coming in, where the intensity remains the same across the profile, but you actually get a variation in the polarization, which changes the orientation of the director of the surface. So going back to the idea of Barrowman's alignment technique, where you have these striations, there was an important paper back in the early 80s by Dave Litster and Hank Smith, and this came out of MIT, the MIT Lincoln Lab group, where they put down a metallic substrate. Now you're looking in, so effectively what they've done over here is they've created striations going into the board, and so you have a low point, a high point, and low point. Notice that there's no rubbing going on, there is no polymer involved in this in terms of aligning the backbone. And they're still able to get pneumatic order where the director is going to lie along the ridges. So that was the first sort of proof of Barrowman's idea. Now this has been taken up, and one of the people who's doing a lot of this right now is Hiroshi Okuyama. He wasn't the inventor of this technique, but the idea is to basically look at stamping, where you have a template, which is a hard template that you fabricate using some sort of traditional technique. You can use lithography, photolithography, you can use EV etching, so on. and then you sort of squish it into a soft material like polymethyl methacrylate that's above the glass transition temperature. You then cool it down, the PMMA hardens, and then very carefully you remove the template over here, and then you're left with what amounts to an image. And you could do this over and over and over and over again. And if you make a large area, you can basically make very, very nicely patterned alignment. One of the things that was of interest here is that they actually achieved, this first group achieved spacings over here as little as 25 nanometers, but more impressively, depths of 100 nanometers. So these are extremely deep wells. And had I thought of it, sorry about this, had I thought of it, I would have put a picture that my wife sent me last night. Anybody ever hear of a sinkhole? The term. That's where the ground gives way. There was one that occurred in Florida a few months ago. A sinkhole swallowed a house, and unfortunately they never found the man who was sleeping in the house, in his house. So there was just this enormous sinkhole that happened out in the street in front of our house, and my wife took some pictures of this. And again, it's, you know, maybe this wide, but it's really, really deep, so it's a little bit like this. It would have been a really nice graphic, but sorry. You can do this nano imprinting on other materials. You could play games by putting different side chains on, so when you do the nano imprinting, you can get different orientations. This was done recently by Blog's group. So he has a nice regular topography over here, but because of the side chain that gives you perpendicular alignment when the liquid crystal aligns over here, you can get a bistable device. And also by changing the structure of the polymer, you can change the glass transition temperature. There are a lot of games that you can play. Another thing that we're beginning to do now is to do electron beam etching. This is where one can put down some sort of substrate. In our case, we're using a conducting polymer, and that was actually one of the reasons I asked the question yesterday about liquid crystals and photovoltaics. So this is where this would come in. And with several steps, you can E-beam over the PMMA that you put on top, then wash it away with the developer. And then, for instance, we coat this with typically SiO2, and then eventually wash away the underlying PMMA. And so what we end up getting is a series of insulating ridges sitting on top of a conducting polymer. And then we can pattern this pretty much any way we want to. We have resolution here of about 50 nanometers right now. Let's say microns. There's a micro-rubbing technique which does not really give you nano patterns at all. But it does, again, show you the alignment of the backbone because you're not creating deep, localized ridges. And so over here you can see that a group of Hanma and Noze from Japan, and very shortly thereafter a group in the Netherlands, plus Greg Crawford, used a large ball and rubbed the polymer. So over here this is relatively flat on molecular length scales. But you are getting the alignment of the polymer backbone using this ball, and that also gives you an alignment. And so this can be moved around any way you want, and you can create these small patterns. I'll eventually get to the way that we do most of our work. There's another technique that was published about 13, 14 years ago out of the IBM group at Yorktown Heights in New York. This was to do ion beam etching of inorganic materials as opposed to a polymer. It made a splash in Nature and then kind of fell flat on its face. What they're doing is they're breaking some of the rings along different orientations and then using the broken ring structure of the surface to give preferential alignment of the director. So this looked very positive at first, but it didn't work. It was a dead end. It's like Betamax or something like that, if anybody remembers the reference. Okay, another thing that was developed from IBM in Zurich was AM nanolithography, and this is the technique that we've been using mostly, although as I said, we're now moving toward E-beam lithography. And so here, what you do is you take an AFM, an atomic force microscope, that has a rather stiff cantilever, ordinarily used in non-contact, or sometimes called tapping mode. You effectively scratch the surface. It effectively acts like a plow. That is, you're taking this tip and you're dragging it or pushing it back and forth on the surface, and you can create patterns that are as close, or line spacings that are as close now as 15 nanometers. This is something that we did a long time ago that's unpublished. So here's a picture of the surface with 50 nanometer spacings. This is the surface that's a somewhat rougher surface with 25 nanometer spacings. We could do 15 nanometer spacings with care on a smoother surface. So it actually looks quite nice. You can also do the plowing sufficiently softly that you barely can detect any topography whatsoever. So with this, we've made things early on. We've made some optical gratings. Here the spacing is actually quite large. So from here to here, the spacing is approximately 2 to 3 microns. We've made other sorts of gratings over here. So this is a grating that is completely independent of polarization. It doesn't matter whether you're coming in with linear polarization, whichever one you want, or right or left circularly polarized light. It's independent of all of that. And the other nice thing is that it's electrically switchable, and it's also quite fast. So you can do things of that sort. Now, another thing that Yokoyama's group did, is Hiroshi here?
No, he's left.
Unfortunately, okay. Okay, well, I may be fortunate, because now I'll take credit. Because Jung-Kyun Kim was my postdoc, went to Hiroshi's group and did it. So Kim learned all the stuff in my group and then brought it to Hiroshi. Anyway, so they had some very, very nice work dealing with both bistable patterns and tristable patterns that they were able to create. And again, this was by AFM patterning. The usable size is again related to the extrapolation length. If you try to pattern on a length scale somewhat smaller than the extrapolation length, you're not going to see much of anything. It's basically going to wash out. So again, you have to be careful about the extrapolation length in the system. And I'll talk about measuring things like that. This is something we're actually spending a lot of time right now, and this is chiral symmetry. And I'll talk a bit more about that either later in this talk or the next talk. And so here you can imagine that we come through the liquid crystal with the AFM, but for each successive line, A, B, C, we change the force. Okay? Now, if you vary the force from A to force A, force B, force A, force B, that's not interesting. But if you do an ABC pattern that requires at least 3 of these, you notice that this looks a little bit like a sawtooth topography, which means that you have a non-centrosymmetric potential. Okay? And this is just different overall forces. So we can create what amounts to surface chirality here. We'll talk about that later. Again, Guo came up with something rather interesting. Instead of just having a single force along the whole line, he actually puts the sawtooth into the force scribing along a particular direction. So it creates a deep area, less deep, and then starts again deep, less deep. And by doing this, he's actually been able to control the pre-tilting of the force.
Just a question about the last slide. Is the height there in nanometers or micrometers?
That's my mistake. That's nanometers. Sorry,
Okay.
yes, that's pretty deep if it's microns. No, it's sorry, it's nanometers. That was an error on my part. Thanks. This is something that looked exciting, but again, I don't think it's gone anywhere. And this is the idea of dip panel lithography with an AFM. And that is, you take the AFM tip, you dip it into some material that's liquefied. It's basically maybe like a surfactant in a solvent. And then you pattern the surface with it. Think about an old type of pen from 200, from 50 or 60 years ago, where you'd have to dip the pen into an ink well and then do some writing until the ink ran out. And you could do this patterning and effectively control things like wetting properties of the surface. So we tried this. This is an ITO substrate, indium tin oxide, and we took the surfactant cesium perfluorodecanoate. I chose that because we were using this for a completely different experiment. It was there in the lab. And we wrote lines over here that had a width of between 75 and 100 nanometers, and we spaced them 1 micron apart. We put the liquid crystal down on the surface. Here there's no alignment whatsoever, but you can see we're getting homeotropic in this region. So it looked like it might be a nice technique, but it doesn't seem to have gone anywhere. I haven't seen anything other than the use of this technique to look at collagen. So what I want to do now is go back and look at a couple of applications of the nanopatterning, at which point I will get to the nanoimaging. And I think I may actually have to jettison some slides along the way. Okay, picture the letter E on a mathematical plane. Have a mirror here coming out of the board. Now look at the mirror image of the letter E. You can imagine that we can take this letter E, rotate it in the plane without lifting it out, and overlap this letter E. That means it is not chiral in 2 dimensions. The letter F, on the other hand, if we try to rotate the letter F in the plane into its mirror image, you can't do that. That means in 2 dimensions, this letter F is chiral. Okay? We'll talk about consequences of that in a bit. Of course, you can take the letter F, flip it out of the plane, and put it into its mirror image. So 3-dimensionally, it's non-chiral, but 2-dimensionally, it's chiral. You go back to the Olympics logo. So last summer, this was a big deal when the Olympics going on in London. You can imagine when you add the colors into the Olympics logo that this is chiral in 2 dimensions because you cannot rotate this in the plane and put it into there. But if you get rid of the color, then it becomes achiral or non-chiral. Chirality shows up everywhere. You have optical rotatory power. Chirality shows up in the body, think of DNA. Most pharmaceuticals are chiral. You have circular dichroism. It's an important property that appears all over the place. And if there are people here who know something about cosmology, there's some chiral symmetry breaking out there. I'm not an expert, and I won't go any further than that. So what we wanted to do is see if we can create a chiral surface. And we want to do this by patterning a chiral surface. So one of the ideas that we came up with was to use a step pattern where we would take the AFM. Okay, so imagine this is the AFM tip. You take the AFM and describe patterns like this, like steps. You see a picture of the AFM surface after it's been described. If we make this vertical distance and the horizontal distance, A and B, the same, that's not chiral, because if you look at its mirror image over here, you can take this, rotate it by 90 degrees, and overlap its mirror image, so that's not chiral. But if A does not equal B, that's what you have over here, there's no way I can take this left side and rotate it into the right side, maintaining that pattern in the plane. That's important, so in 2 dimensions. This is chiral, this is not chiral. If you go to the limit where you have vertical lines, very long vertical lines, or very long horizontal lines, that again becomes non-chiral. So we patterned this, and voila, this is what we have. So here we have a chiral surface pattern. Being careful, it's not 2-dimensional, it's really a 3-dimensional chiral pattern, but localized very close to the surface. So the question is, how do we see this pattern? I mean, how do we see the chirality? And this is where the liquid crystals come in. So there is something called an electroclinic effect that was developed in the late 70s by Bob Meyer and Steve Garoff. And it requires a certain symmetry. But basically, if you have a chiral molecule and you apply an electric field, so here's the molecule. Can you see this over here? So here's the molecule in the synectic C phase. If you apply an electric field over here, this electric field couples to a polarization that has to exist because of the symmetry, because of the rotational biasing of the molecule, and you can flip the molecule back and forth. And in fact, at the very end of the last talk, Professor Crossland talked about the pneumatic versus the ferroelectric type device in terms of image quality. So there is this effect that you have with chirality with the molecules in a certain phase. If you have non-chiral molecules, achiral molecules, sitting at a chiral surface, there's going to be, you can imagine the electric field causes a rotational biasing of this molecule. The molecule can be oriented along the easy axis or tilt slightly in one direction or the other because it's now biased. if the molecule, if the whole system there is achiral, tilting this way with respect to the easy axis is equivalent to this. But if the system is, for instance, right-handed, then the molecule will want to have a specific tilt with respect to the easy axis, so as you come in, it has the appropriate rotation associated with the local chirality. And so by applying an electric field to the molecule sitting at the surface, we can induce a tilt. This is the inverse effect, the electroclinic effect. We can cause the molecules to tilt by a certain amount. If we reverse the field, the molecules tilt in the opposite direction. And so we can do this. It's a relatively simple setup over here. And we do this, we apply different electric fields, and we measure the induced tilt. This is relatively small, so this is something of the order of less than milliradians. And we do this for different ratios of that A to B in terms of making these step patterns. Now, this over here looks like someone took a shotgun. Okay, and this is the data. These are the data. But keep in mind that we're looking at a symmetry breaking effect. And we do have other data for other sorts of experiments where it's considerably cleaner, but this is enough to prove the point. This is sufficient to prove the point. Notice that when R equals 1, that's when A equals B, it should not be chiral. You effectively have all your data is flat. There's no signal to speak of. But as you go up in this ratio, the slope gets larger and larger. But notice what happens that when we go to R equals 13, that is a relatively sharp distance between the vertical and horizontal lines, this comes down quite a bit. And we can ascribe that. So this now here, the data over here show the slope of those lines with very large error bars because of the noise here. You notice that at R equals 1, that should give us no electroclinic effect. That's exactly what we see. When we go up to a very large R, we're getting to have long lines. There's not going to be much chirality, so it's going back down. But notice you get the peak here when you have a ratio of around 6. That's something like what we have over here. What's going on over here is that the little jobs, these little kinks where we have the step occurs, that's what I call a chiral core. As we move away from that over here, because a distance comparable to an extrapolation length, for molecules, liquid crystal molecules in this region over here, they're not going to feel much of anything here or anything over here. So as we increase this ratio larger and larger, these chiral cores are separating further and further apart. And as a result, the bulk of the system is not going to have any chiral behavior. So what we've been able to do here is look indirectly, using this chirality as a measure, at the extrapolation length, which here works out to be about 500 or so nanometers. I'm going to show you other sorts of things later on. Okay, now, one of the things we're doing right now is we're making checkerboard patterns of left and right, and we can do a few interesting things here. One is to do optical separation of right and left-handed materials on the surface. But even more interesting is with Torsten Hagman, who will be speaking, I think, on Saturday, here. He is functionalizing some of our AFM tips with a chiral ligand, left and right-handed ligands, and we should be able to do AFM chiral force measurements going across the boundary and actually looking at a characteristic length scale for this chiral force to take place. This I'm going to skip because of time completely. The next couple of slides just dealt with showing how we can treat smectics as analogous to superconductors, that if you have large bend in smectics, smectics cannot support bend, it melts into the nematic just as in a type 1 superconductor, a large magnetic field causes the superconductor to go normal. So we can do this by creating a large bend pattern. But let me skip over that because there's just not enough time for that. Okay, so now we turn to nanoimaging. And there are various ways of doing this as well. Probably the oldest and best known is X-rays, and I'm not going to touch that. It's just too big a field, and that's worth 2 or 3 semester course just in and of itself. So X-ray scattering is a way of looking at nanostructure. indirectly through Fourier transform, but we're not going to deal with that here. Okay, so another method is freeze fracture and transmission electron microscopy. So about late 80s, Tom Lebensky and his student Scott Wren came up with the idea of the twisted grain boundary phase in a chiral smectic, where you eventually, for sufficient chirality, you get these periodic breaks of layers. There were various attempts to look at this. I think it was first seen using X-rays. But another way of looking at it directly, rather than trying to invert the X-ray pattern, is to do freeze fracture. So they took, this was Zazadinsky, and Budvy's the chemist, Ron Pindak was the X-ray scatterer. They took this sample, twisted grain boundary, they cooled it down using liquid nitrogen. Propane is another way of doing this at a very, very fast rate to lock in the order. And then they fracture it in vacuum and put a material, typically platinum, on the surface that they can then effectively make a replica of the surface that they see, which they can then examine the replica with TEM. And this is what they're able to see. So this image is actually a real space image of what's going on with this twisted grain boundary phase. Now, from what I gathered here, I arrived yesterday, that there's been some talk about confocal microscopy. This is another way of doing things. Confocal microscopy in general, and again, it depends upon the wavelength that you use, but in general, it's a diffraction limited. There's some games you can play technique, but you're typically looking at a couple of 100 nanometers in all directions resolution. There may be other ways that I don't know about, but that's what I know about confocal microscopy. One of the nice things is that it's non-invasive, so you're not fracturing a cell or anything like that. Another thing which is an invasive technique is scanning tunneling microscopy. This is where you have a conducting surface. You put a sample on top of that conducting surface here, and then you apply a potential between some very, very fine tip and the underlying conductor. And when you bring the tip very, very close, the tunneling current depends very strongly on the material through which you're tunneling and the distance that you actually have to tunnel so you can create images. So early on, Binnig, who was one of the Nobel Prize winners for the whole idea of scanning probe microscopy, looked at the liquid crystal 10 CB, and you can see the image is 10 CB on graphite surfaces. So you can see the images over here, and they're able to understand what was going on with the alignment of 10 CB using this technique. Turns out that a slightly shorter molecule, 8 CB, has a different structure on graphite, and in fact on molybdenum disulfide, it has yet a different structure. I have another grad student working at Jussieu right now with Lacaze's group, and what we're trying to do is put down another liquid crystal with a negative dielectric anisotropy on MOS2 and try to create a very localized chiral surface that way. So this is going to be the technique that I'll be talking about pretty much for the rest of my available time. This is using a near-field scanning optical microscope. Sometimes people call it a scanning near-field optical microscope, NSOM or SNOM. And the idea is that if you can keep the top surface open, if you don't need a closed cell, you can bring the NSOM fiber and immerse it into the liquid crystal and be able to make an image inside the liquid crystal. It's invasive. It doesn't work for everything, but it gives you the possibility of some extraordinary resolution. So the idea is that you have an optical fiber that's brought down to an aperture that is sub-wavelength of light, typically 50, 75, 100 nanometers, depends upon how it's made and so on. But you have a sub-wavelength of light aperture. And like any other scanning probe technique, you run it across the surface, very close to the surface. The distance is controlled by a tuning fork mechanism for feedback. And since the computer knows where the fiber is, you can either come in with light through the fiber and have a detector downstream, which is how we do it. Sometimes if you're looking at a reflecting surface, you have to have a detector here. Sometimes you have a broad light from underneath, or reflecting from the surface, and you use the fiber as the collector the light. So there are various ways that you can do this. And then in principle, you can get resolution if you scan the fiber, say typically 2 or 3 or 4 nanometers over the surface, you can get resolution that's comparable to the aperture size of the fiber, which would be an area down by as much as a factor of 100 of a typical optical wavelength. We add a couple of other things to this. We use a light chopper, so we can do this in phase-sensitive mode. We also do this with polarized light. Okay, so the idea again is you immerse the fiber into the liquid crystal. Now, one of the problems with an optical fiber that's sub-wavelength of light is that the light coming out, since it's very small, you have lots and lots of spatial Fourier components. And it turns out that the large Q, that is the short wavelength spatial components, tend to be evanescent, they disappear. So if you go somewhat far away from the fiber aperture, and far away means comparable to maybe twice the fiber diameter, that's not very far, it's like 100 nanometers. You get a spreading and you lose a lot of intensity. That's not good. But if you set up your optics in such a way that you effectively throw away all this other light coming out that's eventually picked up downstream by the detector, you can actually get resolution on the surface. The earlier experiments we did were at about 100 nanometers, and now we're at about 60 nanometers resolution with some improved fibers and control. So again, we have a liquid crystal, we've patterned the surface to create some sort of alignment of the liquid crystal. This is just a cartoon. We bring this into, this is a cartoon of the fiber. We bring it into the liquid crystal. We can scan at one height, then we bring it up a little bit, scan at another height, and we can make images this way in 3D, bearing in mind that we can do this only in pneumatics or isotropic. We can't do this in smectics. You just destroy the layers. So, there are advantages to some techniques over other techniques. But before I go on much further with this, let me just point out a couple of issues here. First, to say, even in a pneumatic, aren't we disturbing the liquid crystal by moving this fiber through? Our original thought was probably, but we tried it, and in fact, we found that there's almost no effect at all, that the fiber does not perturb the liquid crystal very much, and this was also shown by a group in Japan about 10 years ago. What's interesting is that the liquid crystal perturbs the fiber. And the reason is that in the feedback control system, we have to vibrate the fiber very rapidly using the tuning fork. But you can imagine if we vibrated along the direction of the director versus perpendicular, that fiber is going to see a slightly different viscosity. So the feedback is going to be different, and you sometimes have to account for that. Typically, that will have a 1 or so nanometer variation in height control. I mean, there are other issues that we had to deal with the fiber. This is motion of the fiber through the liquid crystal. Does the liquid crystal settle down in time? Here the answer is yes, because on those length scales, the fiber is moving very, very slowly. Our polarization, anybody who does optics seeing an extinction ratio of 60 to 1 will say, this is awful. When you're dealing with a fiber that's 60 nanometers across, that isn't so bad. You can improve this by using a fiber with an anisymmetric aperture, basically an extended aperture. Not circular, but like this, I'm using the word, rectangular aperture. The problem is once you have a rectangular aperture, you lose control over the orientation of the polarization hitting the sample. So there's a trade-off here. Fiber rigidity is another issue. This turned out not to be too important. Temperature control, especially if you're doing phase transitions, is important. Temperature gradient. So how do we get around temperature gradient issues? With Christmas lights. So this is our instrument. We could heat locally, which is something that we're actually doing right now by using a very, very local heater under the fiber, but we wanted to avoid having temperature gradients locally. So the idea is to heat the entire instrument up to a fixed temperature to avoid the gradients. Now, we don't take it up to 100. We go up to maybe 40 degrees that way. But we can do that. We can look at phase transitions and so on. And we use red Christmas lights, and we use a filter, a notch filter in front of, bandpass filter in front of our green lasers. So these lights don't bother us. And unlike what everybody else is using, we are using incandescence here. LEDs would not do the trick. We want the heating. We don't want just the light. Okay, so the first test we did, I'm almost finished with this here. The first test we did is just look at an ordinary pneumatic. We brought the fiber in, and then we pulled it out slowly, and what we measured was the intensity through an analyzer downstream. Effectively, what we're measuring is something that looks like the integrated birefringence, sometimes called the optical or phase retardation of light, as it passes through the birefringent medium from the aperture down to the substrate. And we did this over a relatively large distance. We did this out to about 2 microns, and we saw this behavior over here. We're using liquid crystal 6Cb. So the optics from small apertures is extremely complicated. And if you're going through a birefringent media, it's even more complicated. So just for the hell of it, when we first started this, we said, okay, let's assume we can use a plane wave approximation. It doesn't make sense, but we've used it a number of times, and at least in the situations that we're looking at, it's worked all the time. So I seem to be seeing some weird symbols here showing up. I'm not sure what that thing over is. Okay, so the point is you come in with light, you can make it linearly or circularly polarized depending upon what you set up over here. We actually did this with circular polarized light, and then you can look at the time averaged intensity. It's going to depend upon this alpha, which again is the integral of the birefringence from the aperture down to the surface. You should end up measuring an intensity that's a constant plus something that scales as the sine of alpha, and that's exactly what we saw. We got a nice sinusoidal fit. We know that the phase shift from the minimum to the maximum, that would be a phase shift of pi. We saw that we had to translate the fiber upward 1.56 microns. At that time, we were using an old argon ion laser, which we've given up on, because that was the third plasma tube in 4 years. And they just kept dying. So we switched over to just using diode lasers now. And from this, we can back out the birefringence of 6Cb. There's no interesting physics here. It's just a test. And it was right on target. So that was the first of many experiments that we've done. So some of the other things that we have ongoing now deal with carbon nanotubes and liquid crystals. We're trying to image what's going on, especially if the carbon nanotubes are chiral. I won't talk about this. I will not talk about PMO. But toward the end of the next talk, I will talk about looking at orientational quench disorder with very, very high resolution. So this is sort of the background. The first was to deal with general ways of patterning and general ways of imaging, and I got into the sorts of things that we're doing. The next talk will deal with 4 specific examples of things that we've done or are currently doing. And I'll stop here, and then I need a voice break for a couple minutes. Okay.
Thanks for the first part of the lecture. Does anyone have any questions on this part of the lecture? Yes?
I don't know much about AFM, but isn't it difficult to, because liquid crystals are quite mobile, so isn't it very difficult to look at individual molecules when there's so much movement?
Are you talking about the STM or the AFM? Okay, so what my student Ian now is doing at Shistute, and what was done by Binnig years ago, they were looking at effectively a layer of liquid crystal at the surface that was locked in by the surface. So the surface effectively got rid of the motion that you're thinking about. I don't know if, and even right now, we don't know whether we're looking just at a monolayer or whether we're going through 2 or 3 layers of liquid crystal to get down there. But the layer at the graphene or at the MOS2 is so well locked into place. And you're also not touching, remember, you're above and you're looking at a tunneling current. So it's, for that first layer, it's minimally invasive.
Even at room temperature?
That was all at room temperature. Yeah. We may have some questions about what I'm going to show you next talk, okay, but that's another story.
Okay, thank you.
There's another question there, yes?
And I wanted to ask about the effects of the depth of certain surface patterns? Like
Oh,
do you get much
Okay,
deeper?
so with the AFM patterns, it depends upon what we're doing. Because controlling the depth also controls the strength of chirality, it controls the anchoring strength, I mean, there are a lot of things. So I have worked with relatively shallow depths of 3 or 4 nanometers, and sometimes we've made very deep patterns intentionally, which will go, for us, deep would be about 50 or 60 nanometers. I know Hiroshi Yokoyama has done this with very, very soft rubbing, so that changes the anchoring strength condition. But he found that he could go sufficiently soft that he could not measure a topography within the resolution of his instrument, yet still get uniform alignment with a pneumatic. So the depth, it depends upon what you want, but there's a lot of flexibility that way. If you're doing this with e-beam writing, there you have to rely on the depth, because you're not creating any sort of anisotropic van der Waals interactions by rubbing a polymer. And so there it does rely on depth, and typically the depths we're using there are 12 to 15 nanometers.
Yes.
When you're doing those near field measurements and you're sticking that tip in your sample, do you not get surface effects with the tip and the liquid crystal?
I think I'm going to address that in the second one. By and large, we found that the boundary condition at the tip is not a particular orientation. The liquid crystal we found can adopt pretty much any arc, at least the liquid crystals we've used. There's no particular reduced order parameter, but we have what amounts to something like ds/dz. That is the derivative of the order parameter in, say, in an isotropic phase. At the surface, the derivative has to vanish. And that's, I'm going to mention that a little bit later on with one of the measurements. And all of this is empirical. Presumably, we can functionalize these tips. It's something on the shelf of many projects to do. But we haven't functionalized. We're basically using clean tips, which tend to be aluminum coated with the center fiber.
Yes.
Okay, after the surface chirality is verified, is there any way to determine whether it's left-handed or right-handed?
I'm sorry, yeah, you can do this. This is something that we actually haven't done, and every time I talk about it, that's a question that's asked. The way you would do it is you would take something that's known, and something that's known could be, for instance, using a right-handed surface material, surfactant, for instance, on the surface, and seeing what the sign of the signal looks like. There's another thing that we have done recently, we haven't said left or right-handed. I talked to you privately about that. It's a long, complicated explanation, but we can actually change the sign of the electroclinic effect for a right-handed twisted structure by doping it with a right-handed. I need to talk separately and draw pictures. It's not in this talk. That's a completely different talk. But yeah, it's possible to do.
I had a question, which is, are you going to talk about this last part, which is the nanoscopic Chiral Cores in your next presentation?
I'm sorry,
The last one, which is periodic mesoporous. Are you going to talk about this in the next?
No.
Okay.
Sorry.
So then I can ask a question on that, if that's okay. Which is, essentially, if it's sort of a chiral core, then a molecule which is going in there would have sort of an anisotropic viscosity in some sense, with interacting with the core, and maybe that sort of templates it. So I guess the question, what I would like to know, what exact questions you're asking. Is it the chirality ordering on larger length scales?
What we're trying to look at with this, and it has not been an easy experiment to do. We're trying to understand over what length scale, as we come outside the PMO, over what length scale you get chiral induction by what mechanism. And again, we have other experiments that might actually do it better, but the idea is that I know he was at the Newton Institute. I don't know if he spoke here. Claudio Zanoni from Bologna has done some calculations. He does numeric modeling, atomistic simulations, in which he seems to show that you can get chiral induction. That is, you have a chiral surface and then you have not chiral, 8 chiral molecules above that. You can get chiral induction typically over length scales of about 5 to 10 nanometers. And those are the sorts of things we're trying to measure. It's not easy.
Right. Okay, well, let's thank the speaker for a wonderful talk. And I suggest we break for 5